I work as a postdoctoral research associate at the SNU Center for Basic Sciences, Kolkata. I have obtained my PhD degree in 2018 and I have 2 years of post-PhD research experience. Today I am going to talk about Doppler effect. So let's begin. So first we are going to understand what is Doppler effect. Doppler effect is the change in the observed frequency or wavelength caused by the relative motion between emitter and observer. Doppler effect is widely observed. Most of us have observed it in our daily life. Anything which is moving and emits light or sound shows the effect. We are going to talk about what are the other places where Doppler effect is employed or used. So we have all observed the Doppler effect while standing on a platform when a superfast train is passing by, and we have seen the pitch is going up while the train is coming towards us, and then the pitch goes down. So this is the foremost and probably the most widely observed effect of Doppler effect. Now Doppler effect is also used in Doppler radar system, which uses the tracking of flights, and it can also be used for rainfall and cyclone warnings. As you can see, the image here shows a Doppler image of Kochi. The red dots which are shown here in these places are most likely to have heavy rainfall. Now Doppler effect is heavily used for astronomy and astrophysics, where we measure the Doppler effect for stars and galaxies to understand how the universe is expanding, or the local galaxies are coming closer to each other. So that's a part of astronomy and astrophysics, and it is also used in medical sciences, where Doppler tomography is performed to understand whether there exists any anomaly in the human body or not. Now we want to measure the Doppler effect. So while measuring the Doppler effect, the most general formula is given here. As you can see, this is if we consider the observer and the source both are moving in a collinear direction, then your θ1 and θ2 will be 0. Then the formula will be much simpler. And suppose your source and your observer both are moving towards each other, then your numerator will be v plus v naught and your denominator will be v minus vs. So in that case the frequency will go up, and that is, as the frequency of blue is higher than the frequency of red, when the frequency goes up we call it a blue sheet, and when the frequency goes down we call it a red sheet. The frequency goes down when the observer and source are receding from each other. So in that case your numerator will be v minus v naught and your denominator will be v minus v plus vs. So now what happens when both sources are moving parallelly? In that case there will be no Doppler effect. Now what will happen if your source velocity exceeds the velocity of sound? We are going to see this beautiful diagram here shown. And now, as we all know, the sound speed traveled via creating pressure on the medium. Now if we consider static source, then it will create isotropic pressure contours around it, as shown in figure 1. And if the source is moving, then the pressure contours will come closer to each other in the direction of motion. Now if the source is at the velocity of sound, which is the sonic barrier, then it creates a shock front in front of it, and a shock front usually comes with a sonic boom. Now what happens if the source velocity exceeds the velocity of light? In that case there will be no shock front, as the source has moved farther away before the shock front had been created. So this is it. Thank you, and keep listening me, and I'll post more on relativistic Doppler effects. Thanks.